I'll start again. All right, everyone, welcome back. I am Sarah Peacock. I am an NPP at Goddard and a member of the CHAMPS Consortium, and I will be your moderator for this final session on exoplanet and brown dwarf atmospheres. So up first, we have Lisa Dang, who is a graduate student at McGill University, who will be giving a dissertation talk on characterizing evolving exoplanets and their atmospheres with the Spitzer Space Telescope. Lisa, I will message you when you have both 5 and 2 minutes to go. And with that, you can take it away whenever you are ready.
Sorry, I think finding the unmute button is a common problem that everyone has. So thank you very much for the opportunity to be here today to talk about the work I did during my PhD, and especially a big thanks for the CHAMPS collaboration for organizing this on such a short time scale. So I'm a final year PhD student at McGill University, and today I'm here to present my work on characterizing exoplanets and their atmosphere with the Spitzer Space Telescope. So my presentation is going to follow the journey of a planet undergoing high eccentricity tidal migration. So first, we'll start beyond the snow line with the Spitzer microlensing campaign, and then we'll lose a little bit of angular momentum and be sent on an eccentric orbit where we are going to characterize the thermal phase curve of an eccentric hot Jupiter caught in the act of migrating. And then we are going to tidally circularize our orbit and go through some things that we've learned from phase curves of more typical hot Jupiter or hot Jupiters on circular orbits. And finally, we'll have our atmosphere stripped away and look at ultra short period rocky planets. So along the way, I'm also going to discuss ideas that have emerged from these projects that maybe we'll look at in the future. So today I'll focus mostly on atmospheric characterization of transiting hot Jupiters. So like many talked about today, I'll still remind you of the basics though. So these are gas giants blasted with stellar irradiation, likely synchronously rotating, resulting in a permanent day side and a permanent night side as illustrated here on this slide. Because of the synchronous rotation, we also expect drastic temperature gradients between the day side and night side of these planets. And so as they orbit around the host star, we are going to observe a transit when it passes in front and an eclipse when the planet is eclipsed by the star. But a distant observer will also observe a different region of the planet, causing a variation of brightness over time. And so what I have on the right here is an example of an infrared phase curve of HD 189733b, where we can see the planet's transit, the eclipses at the two ends, but if you zoom in the middle, you also see this modulation here that is caused by planetary brightness variation. And so we can take this phase curve and transform this into a longitudinal brightness profile for this planet. And so what I'm trying to say here is that these phase curves are super rich in information because you get to see the planet's atmosphere as a whole, as opposed to only the day side or the limb of the atmosphere of the planet. Notice here that the peak of the phase curve is not aligned with the time of secondary eclipse, and this is usually indicative of a shift of the hottest region from the substellar point. In this case, it happens before, so it's an eastward hotspot offset. So to detect these phase variation, we first have to go from Spitzer images to a raw light curve like you see at the top here, to a reduced phase curve like you see at the bottom, with the detector systematics decorrelated from the astrophysical signal that we're trying to go after. And so over the years, this has motivated a bunch of decorrelation methods that have been proposed to achieve this level of precision. And so this motivated us to build an automated open source pipeline called SPCA, for Spitzer Phase Curve Analysis pipeline, with various detector models like the ones that I showed earlier implemented to make future phase curve analysis easier, but also reproducible. So working on reducing Spitzer IRAC light curves has made me very well acquainted with many of these techniques to remove detector systematics. And this has led me to a foray into planetary gravitational lensing. So in 2014, the Spitzer Space Telescope was given a new role as a microlens parallax satellite, aiming to obtain simultaneous space-based light curves of microlensing events to constrain the mass and distance of these lenses. So even though the science is quite different here, and the observing strategy is also quite different, similar instrumental effects also plague microlensing light curve. And so we wanted to see whether any of the decorrelation techniques developed for by the exoplanet transit and eclipse community could serve for microlensing surveys. Because sometimes we end up with this scenario here on the screen, where in the residual, you see this red noise, but this red noise could also be modeled by a planetary anomaly. And so we don't know whether these are just leftover detector systematics or not. On the left here is a microlensing event, the same one, but this time we use pixel level decorrelation to decorrelate the detector systematics, and we were able to model out this structure from this light curve, and therefore rule out this planet detection. And so this is basically it for the microlensing portion of the talk. But if this wasn't enough and you want to know more about the Spitzer microlensing campaign, then I'll welcome questions at the end. Okay, so now we know how to clean these data. We're going to go back to phase curve. What can we learn from them? So here, repeated observations of Exo3b eclipses were extensively studied for Spitzer systematics. The reason why I'm interested in this system is not because of systematics, but because of the moderately eccentricity of the hot Jupiter of about 0.3. And so this is perfect for testing some models. So as opposed to hot Jupiters on circular orbits, the distance between the planet and the host star varies across the orbit. So in principle, they could give us insight into how the atmosphere of a planet responds chemically and thermally to the change of incident flux. And so here are the corresponding Spitzer phase curve obtained for Exo3b after we decorrelated the detector systematics. So we compared these with a variety of climate models to constrain radiative and effective properties such as the equatorial wind speed and the extent of the mixed layer of the atmosphere, and those are listed up here. We also used Gaia observations to empirically constrain the mass and the radius of Exo3b again, and to contextualize these quantities, we ran an evolution model for Exo3b and indeed find that the radius of 1.3 Jupiter radius is a little difficult to explain for a planet of almost 12 Jupiter masses in mass. So interestingly, if you add in an additional 20% of the insulation dumped in the interior of the planet, then the radius of Exo3b becomes reasonable. So if there is indeed some internal heating, then the question becomes, how do you generate this much internal heating? And so there are many ways of inflating a hot Jupiter, but here are the two possible main sources of energy, we think. So the first is the eccentricity of the orbit guarantees that Exo3b is experiencing some amount of tidal heating. But in order to generate this much energy, though, it would have to be caught in the few million year window where the planet is rapidly circularizing its orbit. Another hypothesis has to do with the large mass of almost 12 Jupiter masses. And so when you're barely above the deuterium burning limit, it's plausible that it could take gigayears for you to finish burning all of that deuterium. And so the reality might be a combination of the two. So moving on, eccentric planets have transient features that are relics of their evolutionary history. And so I'm hoping that this is something that we're going to be able to explore with Ariel maybe in the future. So Ariel is an exoplanet surveyor planned to launch in the late 2020s. And so in the future, I'll be looking into eccentric planets, and the objective here is to try to design an experiment using these eccentric planets to find out if their climate can tell us something about their past and their history. Excitingly, we'll also have a partial phase curve of HD 80606b with James Webb that are going to be very useful to test the simulations that we are going to produce for Ariel. So now let's look at hot Jupiters on circular orbits. So these are global circulation or general circulation models of typical hot Jupiters that were all done independently. So the background color represented temperature at different location, and the arrows represent the direction and magnitudes of the winds. But one thing that's particular about all of these models, even though they were done independently, is that they all predict strong equatorial super-rotating jets, causing the planet's hottest region to be located east of the substellar point, represented by the yellow dot. And turns out the first few published Spitzer phase curve whose thermal maps, no, they're not here, but the first few Spitzer phase curve all have shown to exhibit some kind of eastward offset or an offset that is consistent with 0. And so these features were largely interpreted as evidence for the feature that we saw in these GCMs. But in 2016, we used the Spitzer Space Telescope and looked at Kuro 2b, and here's the phase curve that we obtained. So note here that the peak of the phase curve is not exactly coincidental with the secondary eclipse again, but rather occurs a couple of hours later. And so this corresponds to a westward hotspot offset of 23.4 degrees, and therefore contradicting the predictions from the GCM, but also published phase curves of other hot Jupiters. And so while this defied the prediction, but also the results we got previously for other hot Jupiters, the westward offset here could be explained by 3 possible scenarios. And so the first hypothesis is clouds covering the eastern dayside hemisphere, hence blocking thermal emission and sculpting the phase curve. However, it's hard to explain how these clouds would have gone there without invoking westward winds. And so the second scenario questions the synchronous rotation of Kuro 2b, which could be possible given the young age of the planet. And so GCM simulations from Rauscher et al. 2013 have shown that when you have hot Jupiters with a subsynchronous rotation, you could end up in a regime with predominantly westward equatorial winds. And finally, one way to diverge from the feature that we see in these GCMs that are pure hydrodynamical simulations are a magnetic effect. And so hot Jupiters can be so hot that you could have a partially ionized atmosphere. And so therefore, if there is a underlying magnetic field, it could interact with the atmosphere and diverge from eastward winds. So while all of these scenarios are quite different, we think that they're possible because they're all connected to the young age of the system, which is why we think Kuro 2b stands out from phase curves of other more typical hot Jupiters. So speaking of other phase curves, there are now enough of them to allow for comparative studies. And so we did a preliminary comparative study here where we looked at the night-side temperature inferred from these phase curves as shown here. And they have revealed there being 2 classes of hot Jupiters. So those with a constant night-side temperature with tantalizing evidence for these night-side clouds that Peter Gao talked about earlier. And ultra-hot Jupiters where the molecular dissociation that occurs in the atmosphere could increase heat transport to the night side. But there are now over 30 Spitzer phase curve, and this data set is extremely valuable. And so in the future, a uniform analysis of all of them and maybe comparing them beyond on other axis, other comparison axis beyond irradiation temperature could be very telling. So finally, another benchmark achieved by the Spitzer Space Telescope was the first thermal map of a super-Earth, the iconic 55 Cancri. And oftentimes the most extreme systems are the most revealing, and many ultra-short period planets have dayside temperature that are hot enough to harbor a molten magma pool. The difference between these objects and hot Jupiters is that they're expected to have lost their primordial envelope, but instead they could have a thin layer of rock vapor outgassed from the molten day side. And so the Spitzer phase curve here, initially published by Demore et al. In black, have shown a 41-degree eastward hotspot offset. And so this is suggestive of very strong heat circulation on the planet, which is surprising for a planet that's expected to only have a thin layer of atmosphere. But another thing that we noticed here when we looked at this is that this offset also seems to coincide with a recurring break in the observations. And so I've been supervising 2 undergraduate students, Samson Mercier and Alex Gass, who have been using SPCA to try to reproduce these results. And so far, the fit that we get is not quite the same. So we'll be looking at this furthermore. So truth is, this is still an active field of research. It's uncertain whether these planets have a substantial global atmosphere extending to the night side with significant background gas, or if they rather have a partial collapsing rock vapor dominated atmosphere. So I'm really excited to say that our proposal to observe 3 full orbits of K2, 141, 1b has been approved for cycle 1. And so hopefully these observations are going to allow us to determine the extent of the atmosphere of K2-141 and maybe even detect the constituent of this atmosphere. And so this is going to be very complementary to everything that we'll learn about 55 Cancri E, which is also a favorite target of cycle 1. But maybe even looking at this atmosphere, we could get maybe some insight into the structure and composition of these objects and maybe understand what influenced this from their past. So finally, I'd like to conclude with the following thought. The history of a planet matters. So through these investigations, we've seen an example of history mattering, first with the potential internal heating of Exo3b and the westward offset of Kuro-2b. And in the future, we may even see how this matters for lava planets. But moving forward, I propose to utilize all of these types of exoplanets as probes for the planet's history. And so up here, I'm leaving a summary of a past project. And so I'll leave the slide up and welcome question. Thank you. And again, I'd like to thank all the organizers for organizing this today.
Great. Well, thank you, Lisa, for a fantastic talk. That was really interesting. First off, we have a question in the chat from Kevin Stevenson, who asks, do you see any signs of variability in the 55 Cancri E phase curve?
No, so far we don't see any signs of variability, but to be honest, we haven't looked at each individual orbits or phase curves, epochs separately. So maybe this is something that we'll look into to figure out whether this is one of the reasons why we're not getting the same fit as Dermoradol.
Let's see, we got lots of questions popping up. Okay, we've got one from Emily Rauscher. Have there been any follow-up observations of Kuro-2b yet to figure out what's really going on?
No, there hasn't been follow-up observations of Kuro-2b yet, but hopefully I'm really excited to see or to get follow-up observations of Kuro-2b that maybe could help us distinguish between the 3 scenarios that I laid out. So whether or not we'll get the same phase curve again, so whether or not there is variability could maybe help us rule out one of these scenarios. And if we do get a spectroscopic phase curve or just even an eclipse mapping of the planet might also help us distinguish between some of the 3 scenarios.
And then Luke Boma says, great work and great talk. For Exo3b, what are the estimates for the circularization timescale? Is there any chance at observing the eccentricity evolve?
Yeah, maybe I can go back here to the slide. So the time for circularization timescale for Exo3b here is within the first giga year of the planet. The planet's orbit should have circularized already. And so, yeah, I'm not sure. No, sorry, this is the radius. This is another plot. But yeah, so within the first giga year of the planet, we think that the planet's orbit should have circularized already. But the fact that it's a 2 giga year system with still an eccentricity, that's surprising.
And we've got a little bit more time left. So I was wondering if, oh wait, there's another question first from Tad Komachek. Thank you for the comprehensive talk. One thing that popped out to me from the recent Bell and Deng work is that Kuro-2b is not alone in the Spitzer sample with a westward phase curve offset. Do the planets with westward phase curve offsets have any properties in common?
Yeah, I haven't looked into it so far, but maybe that would be that would be an interesting comparison to do, to look at the object with the westward offset and see what sort of particularity or particular properties of this population stands out, and whether or not there is some common property here that we can see in these westward offset hot Jupiters.
All right. Tad says thanks, and I will thank you on behalf of everyone here again for a wonderful talk, and we will switch over to our next speaker. We have Trevor Foote up next, who is a graduate student at Cornell, who will be telling us all about the emission spectrum of WASP 79b. Trevor, whenever you're ready, you can take it away.
Perfect. Thank you very much, Sarah, for that wonderful introduction. My name is Trevor Foote, and today I'm going to present some work that I've done with my advisor, Nicole Lewis, that recently got published on the emission spectrum of WASP-79b using Hubble Space Telescope. So first off, why should we care about WASP-79b? Well, its physical properties happen to place it in a particularly unique transition region of size and temperature phase space that makes it an interesting test bed to study things like cloud formation in the atmospheric regions that we can probe with transmission spectroscopy, as mentioned previously today in Peter's talk, as well as dayside atmospheric thermal inversions that are probed via eclipse observations. And so WASP-79b is a key target to this community to better understand the processes that are shaping the thermochemical structures and cloud formation in hot Jupiters, which we can then use to better inform our atmospheric models. The data I used was part of the panchromatic exoplanet treasury. And this particular data set was rather challenging in regards to the data reduction and systematics. But for the sake of time, I'm just going to skip over that portion today and just show a quick look at a white light curve that came from this data to sort of give you a sense of the signal to noise we're dealing with. And if you're interested to know more, I'll encourage you to look at the paper, which I'll provide a QR code at the end of the presentation for, or reach out to me and I'm happy to discuss further. But once we've cleaned up the data, we then ran it through MCMC to try and extract secondary eclipse times and eclipse depths. And we did this for a number of different scenarios. So in the first one, we fixed the secondary eclipse time, and then we let it be a free parameter and looked at the differences. And we saw about a 5-minute difference, which may suggest a hot spot offset in the atmosphere from recirculation. And then from there, we took the data and binned it down into 3 spectral channels at 1.18, 1.38, and 1.58 microns to try and probe the in and out of the water feature that we expect at 1.4 microns. Once we have those transit depths or the eclipse depths, we then combined our data with the Spitzer data points that were found in Gerhardt et al. In 2020. So that's at 3.6 and 4.5 microns, and then tried to see what we could say about this planet in its atmosphere. So the first thing we looked at was its temperature, and it seems to be consistent with existing literature of black body between 18 and 2000 Kelvin. So then we did a reduced chi-squared comparison using Atmo's library of forward models to look at atmospheric properties under a number of different assumptions. The first was an atmosphere and chemical equilibrium. And here we found that the best fits were those of atmospheres that had solar metallicity and solar C to O ratio with a recirculation factor of 0.75. We then looked at chemical disequilibrium situations. And here we found that there's a number of chemicals that might explain our observations, including iron hydride, VO, or an enhanced H-, which is in line with previous works, such as Rathke et al. In 2021 that saw an enhancement of H- at about 10 to the minus 8. So that's in good agreement with ours. And we actually might see a bit more of an enhancement in the dayside atmosphere versus the limb that was shown in Rathke's paper. And then lastly, we wanted to see what clouds might play or how clouds could play a role in what we see. And with that, we used Virga. And here we see that there's a degeneracy in the recirculation factor when we take into account potential clouds. So if cloudy atmosphere with a recirculation factor of 1 looks very similar to a cloud-free with a recirculation factor of 0.75. But as you can see in the highlighted version or section with HST wavelengths, we could break those degeneracies with additional observations. And so future work would require additional observations, either with HST or James Webb, at these lower wavelengths where we can break some of these degeneracies and finally unlock what WASP 79-9B's atmosphere is all about. And with that, I will turn it back over for questions. Thank you.
All right, thank you, Trevor, for a great talk. While we wait for some questions to pop up in the chat, I'll start off by asking if you have any plans to get those observations with Hubble or James Webb in order to help distinguish which is the most accurate model.
Yeah, so I definitely put in a proposal last year, but it was about the same time as these results were coming out. And so I did not put a lot of effort into that proposal. So I'm planning on resubmitting this year with the hopes of getting some additional time on Hubble, and then the next James Webb, definitely try and submit for there as well.
All right, well, good luck.
Thanks.
All right. Are there any other questions? All right, see if there's any in the here. Okay, well, if there are no other questions, we can get set up for our next speaker. Or I guess I should thank Trevor again.
Thanks.
And next up, we are welcoming back Jason Williams, who is a grad student at Carnegie, who will be giving a dissertation talk on the design and construction of his near-IR spectrograph called Henrietta. So.
Okay, 1 second here.
Yeah, take your time, take your time.
Okay, can you see my screen?
Yes, but there is, yes, now that's perfect.
Okay, great.
And I'll send you a direct message as well with a 5 and 2 minute warning.
Okay, great. Thank you so much. All right, so yeah, so thank you, Sarah, for the introduction, and thank you again to the Champs Collaboration for organizing this great seminar. So my name is Jason Williams, and I'm a 5th year graduate student at the University of Southern California in residence at Carnegie Observatories. And today I'll talk to you about a new near-infrared instrument that we're building to detect exoatmospheres named Henrietta. And I work on this with my advisor, Nicholas Konadaris, and a few other people at Carnegie, Tyson Hare, Johanna Teskey, and Daniel Carlson. And Johanna Teskey is not at Observatory, she's at Earth and Planet Labs. Okay, so I guess the outline of this talk would sort of be, I would first describe what is Henrietta, why do we need it, what makes it unique, and sort of what do we gain if Henrietta is a success. And so first of all, Henrietta is a near-infrared spectrograph that has access to a wavelength range of about 600 to 2400 nanometers, a field of view of 25 by 3 arc minutes, and a nominal spectral resolution of 100. And it's going to go on the 1 meter Swope telescope at Las Campanas Observatory in Chile. And it's designed primarily to study exoplanet atmospheres. And so I designed all the optics, the mounts, and a few of the mechanisms, and I won't be talking about any of that today. But if you have any questions about any of the internals, I'm happy to answer any of those questions. And so one quick initial question that I get a lot is sort of why would you put an exoatmosphere instrument on a 1 meter telescope when we care a lot about signal to noise? And so the biggest reason in its conception, in Henrietta's conception, was that you could really just get a lot more telescope time on a 1 meter telescope than you could get even on a 2 meter telescope. This actually ties a lot into why we actually need an instrument like Henrietta. And so to date, there have been nearly about 4,000, actually close to 5,000 planets confirmed, and close to 4,000 transiting exoplanets. But yet we've only examined a little over 100 of these planets spectroscopically. And that's primarily because there's really no general instrument to observe exoplanet atmospheres. There's plenty of instruments that do it and do it well, but no one dedicated exoatmosphere instrument right now. And so in order to understand to advance our understanding of exoplanets, particularly in a statistical way, we need a way to routinely observe exoplanet atmospheres, and this is exactly what I designed Henrietta to do. And so sort of the challenge of detecting exoatmospheres is twofold. One, you need to be sensitive enough to detect the drop in flux due to the planet, but also to then detect the wavelength dependent absorption in the atmosphere. So what I'm trying to show here is just the two different signal to noise regimes that planet detection and atmosphere detection is in. And so I guess what makes Henrietta unique is the fact that it's designed with a noise budget in mind, a photometric noise budget in mind. And so, so here's a noise budget for a typical, say, a resolution of 100 near-infrared spectrograph on a 1 meter telescope. What we can see here is that the precision, especially for the brightest, highest signal to noise targets, we're at a precision per minute of around 2,000 to 3,000 ppm, or 2 to 3 millimags per minute. And so this is often enough to detect planets on the ground, and this has been done before, but it makes it a little bit of a challenge to detect atmospheres at low resolution. And so we really want to try and aim for the sub 1,000 ppm per minute mark. And so in order to do that, we really need to actively mitigate some of these noise sources. And so from this plot, you can see that there are a lot of noise sources, and these are really just the most dominant ones. And so I just want to highlight here that there's a lot of room for improvement. And so in blue, I'm showing the photon noise, which is the fundamental limit we can do, and it's compared to, again, the total noise for a typical near-infrared spectrograph on a 1 meter telescope in purple. And so if we want to focus on the highest, most ideal signal to noise targets, which are the brightest stars, of course, we're really going to need to focus on two noise sources in particular: subpixel noise, or what I'm calling here subpixel jitter, and scintillation noise. And so here I'm showing simulated data from Schlauen et al. In their paper in 2020 of the subpixel variation of an H2RG detector, which is the standard infrared detector in astronomy. And on both axes, I'm showing 32 subpixels, where 32 subpixels is equal to 1 18 micron pixel. And so on the left, if we look at if we look on a pixel scale and illuminate our detector with a uniform source, this is what we typically do. This is what you'll see. But if we have the capability to measure it on a subpixel scale, there's actually a ton of structure. And so what this really means is that the flux recorded changes depending on where in the pixel photons land. And so for really trying to measure these really small hundreds of ppm signals, this effect really matters. And this effect isn't seen in H2RG detectors before. And so how this really introduces noise is as the PSF moves around on the detector due to the telescope, the atmosphere, temperature fluctuations. Any place where there's a slope, you'll induce often very large variations in the flux on the orders of hundreds to thousands of ppm. And so there are ways to, I guess, correct for this in software using sort of the famous pixel level decorrelation. But for Henrietta, what we plan to do is to use a beam shaping diffuser in the light path that will spread out and average over these subpixel variations. This technique was actually pioneered by Stephenson, Gummy Stephenson, in 2017. And this has worked tremendously well for ground-based photometry. But this would be its first implementation in a ground-based spectrograph. Okay. And so just here, I'm just showing just a cartoon layout of where the diffuser would go. So we currently have two locations for diffusers where we have multiple diffusers. And one has its place in the collimated beam right before the grating. And then the other one, it's not documented here, but it's going to go sort of where this fiber mounted block is in here, sort of in the converging beam right before the detector. And so that's the main reason for that choice is sort of to just have control over different types, or to have the opportunity to use different types of diffusers. And again, I'm happy to answer any more questions about the types of diffusers we'll use later on. And so hopefully this next video, what I'm trying to show here is a simulation of what I've done is, I've placed a typical 2 pixel wide Gaussian PSF, and then a diffuse PSF that's about 10 pixel wide top hat. And I just move them to the same locations, and I just record the differential flux. And what you can see is in red, hopefully I'll let it play again. And what you can see here in red is that for a typical focus PSF, you get a much larger flux variation than you do when you average over the subpixel variations with a top hat. And so my simulations have shown that on average, we can reduce these subpixel effects for our various top hat sizes by about a factor of 10. And so that's great. And so now our next step is we need to work on mitigating the scintillation noise, as this is still a very large hindrance to the spectrophotometric precisions of bright targets. And so, scintillation is caused by the fluctuations across an aperture due to turbulence in the atmosphere. And sort of these intensity fluctuations are propagated, from the start of the atmosphere down to the telescope aperture. And so this is sort of the opposite of seeing, where seeing, in most of the variations are, due to sort of a ground level and not really high above in the atmosphere. But scintillation is, caused by the propagations of these intensities throughout our entire atmosphere. And so my plan to reduce this actually exploits the wavelength independence of scintillation on large telescopes. And so actually most of us are actually very familiar with this with the wavelength dependence of scintillation, because sort of if you look at a star as it twinkles, you can see with your eyes how it changes color ever so slightly. So this is because our eyes are too small to capture the light from all of the different colors as it's refracted and corrupted by the turbulence in our atmosphere. And so if you actually have a statistical model of what the index fluctuations in the atmosphere look like, you can actually calculate the intensity fluctuations and then therefore the correlations between two different wavelengths for various different aperture sizes. And so this idea has been in the optical literature for a while. It's most recently been brought back as early as, I guess late as 2012 by Kornilov et al. And so what I'm trying to show here is that for a given turbulence profile, and if we try and observe this turbulence, if we observe a star with our eye through this turbulence, we get a very small correlation coefficient, around 10 to 20%, sort of looking at different wavelengths. So the wavelengths are not very highly correlated. But for meter class telescopes and beyond, scintillation becomes nearly wavelength dependent and reaches correlation coefficients exceeding 99%. And so what I'm showing here is now that same turbulence profile, but viewed with a 1 meter aperture. And so what I'm showing here is that, across nearby wavelength bins, a common mode signal develops. But the key thing here to recognize is that this only presents itself when scintillation is the most dominant source of noise. You wouldn't be able to detect this common mode signal if you have other large sources of noise. And so again, the only way we'll be able to see this is once we have eliminated all sources of noise. And so then, when we do that, if we're able to mitigate both subpixel and scintillation noise after factoring in the brightness from a comparison star using differential spectrophotometry, that's also again undergone both of these noise reduction techniques, we sort of get our final noise in purple. And so after all of this noise mitigation, we expect a 2 to 6x improvement, depending on the host star magnitude, which is really great. And so I'll just wrap up a little bit here. And so with Henrietta, one of the things I'm most excited to use it for is to perform a large statistical survey of exoatmospheres in the near infrared. Here I'm showing some example targets that span a wide range of radii, less than 10 J magnitudes. And so in red, I've blocked out all the planets that we suspect to have too small of atmospheric features to get a reasonable signal to noise in about 4 transits. So you can see that we still have plenty of targets to choose from to perform a wide survey with, and a lot of the most interesting of these targets can definitely be followed up with JWST. And so let's say even if Henrietta doesn't quite achieve its goals, what perhaps might be its most lasting legacy is it will be to inform the next generation of ground-based instruments. And so what I'm showing here is the predicted data from an in-the-works instrument at Carnegie called MIRMOS. And that's going to go on a 6.5 meter telescope, and it's going to be designed with a lot of the same heritage and lessons learned from Henrietta. And so just a quick status update. So we've ordered everything. So we've ordered all the parts. That took place from April of last year to December of last year. And now we're currently in the lab integration and testing phase. We're currently manufacturing all the mounts. Our doer is being produced by Universal Cryogenics and is on the way. We have the H2RG in possession, and then we're still waiting on the optics and the prism. And so we plan to, I guess, finish this phase out up until August of 2022, and then plan commissioning somewhere in late this year. And so yeah, just to conclude, Henrietta is a near-infrared wide field low resolution spectrograph designed specifically to study exoatmospheres. Instruments like Henrietta are needed to keep pace with the rate at which we discover planets and advance our understanding of their atmospheres. Henrietta will incorporate a beam shaping diffuser and apply novel scintillation mitigation techniques. And sort of with its abundance of telescope time and tremendous precision, Henrietta is poised to significantly advance our statistical understanding of exoplanet atmospheres. And with that, I will take any questions.
All right, thank you, Jason. That was a wonderful talk. We've got tons of questions that are popping in. So first, Robbie Wilson says, great talk. I have 2 questions. First, I'll just read them one at a time.
Okay.
So to reduce scintillation noise, would it be advantageous to have several small aperture telescopes rather than a single meter class telescope similar to Dragonfly?
Yeah, that's a really good question. So I think the biggest advantage of that would be, so yeah, I guess the biggest advantage of that is you actually, if the telescopes are close enough together, sort of like in Dragonfly, I think there's a regime where the scintillation is not only wavelength correlated, but also spatially correlated. So you could really, really remove a lot of the scintillation. But I wouldn't say, beyond that, I wouldn't say it's, I mean, yeah, I guess, yeah, in that respect, yeah, I think it would be slightly more advantageous. But I remember doing this calculation about like a year ago, and I don't think it was only slightly more advantageous. But it was, I think it is more advantageous to do it that way, yeah.
All right, great. And second question, are the beam shaping diffusers cryogenic, and do they operate similarly under these conditions?
Yeah, so that's a great question. So yeah, it's a current topic of research that so we have several different diffusers for this exact reason. So one of the vendors that we're going to produce these diffusers from, they aren't sure if their diffuser works at such cryogenic temperatures, and so and their diffuser is a sort of like a micro lens diffuser. And so they're working on it. They're doing sort of their own internal study. But we also have a few other different diffusers that are sort of refractive diffusers, and we know that those will work at cryogenic temperatures.
Great. Andy McWilliams says, a really great talk. Can you say more about why you have 2 top hat diffusers? What are their differing functions? Also, I'm a little confused as to how scintillation affects the exoatmosphere spectrum. Could you explain it to me more? Thanks.
Yeah, sure. So we have 2 top hat diffusers because just because I guess this is the first time we'll try this in a spectrograph. So we sort of just wanted to try multiple different ones. And whoops, my camera just went out, but I'm still here. And so we wanted to try multiple different ones. And so that's really the main reason why we're having it. And so we wanted to try, I guess the biggest advantage of having it in the converging beam in front of the detector is sort of you can move it left and right a little bit, and you can change the spot size on your detector, and so you can actually increase your resolution, increase or decrease your resolution. So that was one of the main reasons for having 2 different ones. In the collimated beam, you can't quite do that, but it's further away from the detector, which makes it easier to design. And so the impact of scintillation on the exoatmosphere spectrum. So I typically see scintillation as sort of it's a zero mean process. So to me, it shouldn't add any signal. It should only add fluctuations on top of that signal. And so I don't know of any of how else it would. I don't think it would induce a signal. I think it would just reduce the precision. So precision, not accuracy. But I hope that answers your question, and I think that's right. Yeah.
All right. Next, Brad Henson says, most of your error budget focuses on instrumental sources, but having tried exoplanet transmission spectroscopy with Keck myself, I can tell you that variability in the telluric lines is the main problem. Can you say more about how you plan to mitigate atmospheric variability with wavelength?
Yeah, so I mean, so that is a great question. So I think that the main thing here is that, so I guess from all the simulations I've done, is that if you tend to focus on, brighter targets, we've done simulations where, we really increased the variability in the night skylines. And from our simulations, it doesn't quite seem like a problem as long as we focus on brighter targets. The biggest problem that we saw was that if since we're using a wide slit, what happens is you get fringing due to like certain parallel plate optics, and so that then hinders your ability to do like accurate sky subtraction. And so we just mitigated that by sort of having wedge substrates that pretty much completely remove this fringing. But again, this is sort of our first time, I guess, doing this, and it hasn't worked in the past. So I'm very open to, I guess, maybe having a chat with you and just sort of if you could like describe your experiences, because yeah, we're definitely very we want to know all of the possible sources of instrumental problems, and so yeah. But I guess from our simulations, it didn't quite appear to be a problem so far, I guess.
All right, and then final question from Aaron May, or it's a double question again. How many nights per year do you expect to dedicate to Henrietta observations? And with that, how many planets are you hoping to characterize?
Yeah, so that's a good question. So on the slope, you can get a ton of observational time. There's only one instrument on it right now. And I think that last year, even though it was COVID, or it still is COVID, I think it was used maybe like, I want to say like 2 months out of the year. I could be wrong about that, but I remember the last time I checked, it was used 2 months out of the year. So nominally we're baselining sort of 100 to 150 nights per year, but this could exceed and get up to 200. And so we plan, if we want to use the full wavelength coverage, you need to observe with 2 grisms, so you need to at least make 2 trips per planet. And so we're we plan to observe each planet multiple times, and so we sort of baseline anywhere between like 40, I would say like close to 30 and 50 planets per year. I would say not pretty conservatively, but somewhere in the middle. Whereas sort of on our, if we get in an ideal world, maybe we're around like 70, and in like in a worst case scenario, I guess we're closer to 30.
Alrighty. Great, Aaron says, awesome. Looking forward to seeing results, as I think we all are. With that, thank you again, Jason, for a fantastic talk.
Yes, thank you.
We will get ready for our final talk for this session. So Johanna is a postdoc at the American Museum of Natural History, and she'll be telling us about Spitzer observations that revealed the stormy and turbulent nature of giant exoplanet analogs. All right, Johanna, whenever ready.
Great. Thank you so much. And thank you for the opportunity to speak today. It's so exciting. So yeah, today I'm going to share some highlights from our latest program to reveal the turbulent and stormy atmospheres of isolated giant planet analogs. All of our data was taken using the Spitzer Space Telescope, which you can see kind of gracefully slewing in the background there. And there we go. Our study focuses on the atmospheres of young brown dwarfs, which can be viewed as exoplanet analogs. They have overlapping temperatures, radii, masses, and ages. However, since they're isolated, they're nowhere near a star, it means we can observe them in really exquisite detail. And by focusing our attention on these isolated giant planet analogs, we can set some expectations for future observations of directly imaged exoplanets. And one of the technique we used, if my video will work, The technique we use here is called photometric variability monitoring, which basically means tracking the brightness of this world as it rotates. If a planet or a brown dwarf has atmospheric features, such as a large cloud, we can infer its presence by looking for fluctuations in brightness as it rotates in and out of view. And it turns out that Spitzer was pretty much the ideal instrument for carrying out these observations on isolated worlds. I'm going to show you a video here that will kind of orient you with the full population of brown dwarfs we know of, as well as the sample of brown dwarfs that have specifically been targeted for variability with Spitzer. So we're going to start at home on planet Earth and then zoom outwards. And this video here was created using OpenSpace, which is an open source data visualization software developed here at the museum. And we zoom out, you'll start to see the orbits of some of the planets come into view, and eventually we'll kind of bid farewell to the solar system. In the background, you can see stars, which are colored by their temperature. So the hottest ones are white. And the currently known population of brown dwarfs is shown in red. That blue grid that just popped into view is just there for scale. The solar system's at the center of it, and it measures about 100 light years across. So you can see that we're completely surrounded by these brown dwarfs, and this video nicely shows how close they are to us. Now I'm just highlighting the 100 or so brown dwarfs that have been targeted for photometric variability with Spitzer. Next, I'm just going to highlight the objects within the sample that are young. And as I mentioned previously, these young objects are particularly telling about the potential weather conditions on directly imaged planets. So for this work, we spent almost 600 hours staring at this population of young brown dwarfs with the Spitzer Space Telescope to look for clouds in their atmosphere. And we detect cloud-driven variability in a large number of our targets. Here I'm just showing you some of the variability detections so you can get a feeling for what the light curves look like. And they all show these significant fluctuations, which are indicative or suggestive of clouds rotating in and out of view. And by comparing our new measurements with the rich literature of brown dwarf variability studies to date, we were able to compare the young and old samples to try and find some interesting results. The first result I'll highlight is that we found evidence that the young giant planet analogs show enhanced variability compared to higher mass field brown dwarfs. And we see this enhancement in variability in two ways. First, in terms of the variability occurrence rate, which I'm showing on the left. So what percentage of objects show variability that you can detect. But we also see enhancements in the amplitude of variability. So by how much are these objects varying as they rotate? The second result I'm going to very briefly highlight is that we can begin to trace the angular momentum evolution of brown dwarfs, of isolated giant planet analogs, and of giant planet companions as a function of time. So we can literally see all of these populations spin up with time as they contract. And there are lots of takeaways from this plot, but I think one particularly interesting one, especially for the exoplanet people, is that if you look at the companions on this plot that have measured rotation periods, which is not very many objects, so they're all named here. They're the objects with their names attached. But these companions all fall exactly where you would expect them to fall if they were just isolated objects. So if these two objects actually have different formation mechanisms, then that is no longer evidence from how fast they're spinning. And our results are exciting because they set really encouraging expectations for future studies of directly imaged exoplanets with the James Webb Space Telescope. On the right, I'm showing you one particularly exciting system which will be targeted. This is the HR 8799 system of 4 giant planets. And because we've spent literally thousands of hours with Spitzer studying these isolated worlds, we know exactly what to expect for the directly imaged exoplanets as we take our next steps. If any of these results have kind of piqued your interest, then please check out the paper which is published and on the archive today, or else do reach out to me because I'd be really happy to chat more. Thanks so much for your time, and I'd be happy to take any questions.
All right, thanks, Johanna. I will start off the questions. I think you kind of covered it already in that slide previously, but could you further explain like how you age date the brown dwarfs and what ages you consider to be young versus old?
Of course, yeah, no, I didn't mention that at all. So the brown dwarfs in our sample, the majority of them are members of young moving groups. So we can tell from their kinematics combined with their parallax, radial velocity, proper motions, that they're members of a group of stars that all formed together. So when you do locate brown dwarfs in these young moving groups, they have really well-defined ages. And we also have a secondary indicator of youth, which is looking at signatures in the spectrum. So you can look for specific signatures of low gravity in the spectrum. So if you can find an object that's in a young moving group and has these signatures of low gravity, then you can be very confident that that is a young planetary mass object.
All right, Mike Line says, great talk. Any plans for near IR follow-up, or does that data already exist?
Ooh, good idea. I don't think near IR follow-up exists for any of the new objects in the sample, but following up a lot of these objects with HST, spectroscopic variability monitoring, would be incredible, because that is really the way that you can, really say what is causing the variability in their atmospheres. With Spitzer, we're kind of just assuming because of their temperature that it's clouds causing the variability. But if we could get spectroscopic monitoring, we could tell you that it is clouds, what the clouds are made of, and all of that. So yeah, great idea.
Great. Yeah, Mike emphatically says, do it. All right, Ben Lou says, great talk. Do these variable objects have V sin I measurements as well?
Yeah, so that is something I am actively trying to get. Just for context for everyone, if you have a rotation period, you can combine it with a V sin I to get the viewing angle of your brown dwarf or isolated world, whatever you want to call it. So yeah, I'm trying to track down the V sin Is of all of our variable objects to try and look into that.
Alrighty. So with that, I will say thank you again to Johanna, and thank you to all of our speakers from this session. This has been wonderful. And unless there are any announcements from our organizers, I think we're going to break for almost an hour, returning at 3:30 Eastern, if that is correct. I think, yeah. All right.